Hello, I'm going to try to fix stuff. I got a bit ahead of myself on this one. You can see it's already disassembled. What we have here are two Bowmar 901bs. You can see the front there. There's one, and this is the other one. One of those branded Craig, but that doesn't matter. They're Bowmar made the calculator, and they branded it under 3 different names. Don't remember who the third name was, but they're all the same calculator. And actually, this one, if you look at the back here, it says Craig there. So this one, I actually changed the Bowmar front over to this one, just because I like it better. I would have changed the back over too, but this is a slightly earlier revision. This is a revision E, and this is a revision F. So the fronts are the same, but the back is different between the revision E and the F. The revision E back has the diode for the rectification for the charger on 2 posts here, while the F has it up here on the board. So yeah, there's no post on the Bowmar back to put a diode on, so just left it that way. Anyway, the issue is neither of these work. This one, when I got it, it did work, and it kind of went downhill from there. This one, when I got it, it didn't work. And I think what happened to this one is somebody plugged in the charger with the batteries, the original batteries completely, dead, and it just fried the chip. This one, it'll turn on and it'll display at 0, but as soon as you press any key, it just shows the error symbol. And I did do some experimentation. I tried taking, this one, the board actually comes off the keyboard. So I thought, well, maybe there's something wrong with the keyboard. So I did try just jumping the, taking wire and jumping in between the 2 pins to trigger a keystroke on the same thing. So either something on the chip is shorted, or it lost debounce, or I don't know what, but yeah, so this one doesn't work. This one I'm hoping that I can get to work, because I think the issue is in the power supply. I've already kind of diagnosed it. Wasn't really planning to make a video on it, because when I first noticed the issue, I thought, well, let me say what the issue is. The issue is, how it started is, when I got this, and it would turn on and it would work, but the low battery indicator was always on. And so I thought, well, maybe it needs to charge. So I let it charge for quite a while, and no matter however long I let it charge, the low battery indicator would not go out. I later traced that down to the wire for the low battery sense. I just lose focus here. What's going on? There we go. The wire for the low battery sense was disconnected. That's this wire. So this was just broken off right there, and there was nothing connecting that at all. So I had attached this wire. It used to be in one piece when I first made it. And around that same time, I noticed that when I turn it on, the power supply, which you can see on this one, how it's got a complex power supply, would make like a high-pitched whining noise, kind of like it was, under too much load. And the calculator would work fine for maybe a few minutes, and then it would start acting up where it would like clear itself out or not display the correct thing. So my first thought was maybe, well, these batteries, are much better than the original batteries were. So I thought, well, maybe these batteries are holding a much, greater charge than the original ones would have back in 1971. And so maybe the higher output of these batteries was too much for the power supply to handle. Was my initial thought. I also started seeing if I could reflow some of the solder joints here, because they're pretty corroded. But after cleaning them up, they actually don't look like the joints themselves are that bad. And I got some flux stuff and trying to reflow some of them. But these were much worse. These were all green and crusty. But after cleaning them up, they don't actually look like they're the problem. So the next thing I did was, since I have 2 boards here, I just used jump wires to connect the batteries from this calculator to this calculator, because I know the power supply on this one works, it's just the chip doesn't function properly. And I'm taking some voltage measurements here. I got about 7 volts, I think 7.6 volts coming to the chip. on this one, I was getting all kinds of weird readings. So that it's so convincing that the power supply was the issue. And then what started happening, it started getting worse. So, like I said before, when you turn it on, it would work fine for maybe a few minutes or so and then start acting up. But now, I can show this here maybe. I can turn this on. See, as soon as I turn it on, it doesn't want to do anything at all. And I'll show if you can hear the high-pitched whine. So, yeah, it started getting worse. Like I said, the voltages were all off. And so what I eventually started doing was taking some ohm meter measurements. So I suspected that maybe something was starting to short. So if we turn this on and put it in a visible location, which that is not really. It's going to be hard to get everything in shot here. So if you look at this board, right there is a minus, and right there is a plus. Oh, that's in focus. So that's the main output, I believe, from the power supply. I'm thinking about maybe reverse engineering this whole board just to get a good schematic of it, just in case anybody else has issues with theirs and would like a schematic, because I don't think there is one available. So maybe we'll do that. Anyway, if we go from here to here, we get just charging up like a cap, right? Kilo ohms, going up to mega ohms. So that's charging up. Now if we take the same measurement on this one, from here to here, we've got 1.3 ohms. So yeah, I'd say that's a problem. And if we lift this up and have a look, what just so happens to be right in that area is a lovely little tantalum capacitor. And I'm sure most of you guys know these things love to short. UXW Bill aptly describes them as tantrum capacitors because sometimes when they short, if there's enough current, they'll literally just explode into a million pieces. They're not like electrolytes where they'll just pop the top. These things actually burst and you get little tiny crumbs all over the place. But I think this power supply doesn't have enough current to blow it. So I think what we're going to do is take this board out and just clip that guy off and see if our resistance reading changes. Because if it doesn't, then we kind of have a problem. And actually I have to take this whole thing out. Because on this one, the keyboard is socketed, so there's pins here and then there's lower sockets on the keyboard. This one is not, everything's all soldered together. So this one, I have to take the whole thing out as a unit. And if I clip this capacitor and the short goes away, I think what I'm going to do, at least for now, for testing, is just pull the cap from this one and tack it in here and see if the thing works. Let's see, is that? No, I have. There's two more here yet. On both of these, there's supposed to be plastic hold downs up here too on the display, but those are mostly crumbled. You can see here there's supposed to be two little fingers that come out to go around this screw, but they're just completely gone. We can lift this out now, like so. You can see our little fun down in there, so see if I can, is that the one, or is that the one? This might be more difficult than I was anticipating. I thought I'd have more space in there. Let me see if I can get in there and clip that guy off and see where we go from there. Well, that wasn't it. You can see I pulled the cap out. Come on. It's like, what does it say, 6.8 at 16 volts. The short's still there. So a little bit more checking. you can see the only other things connected to those points, or well, there's a couple of things. This side here goes right into the coil. You can see this post right there. That's one of the posts. That's this post right here on the coil. And also goes through this, and you can't really see it, but there's a trace here under the coil, which comes down to this, which goes to ground. So the positive side is actually ground, which is kind of interesting. There's also diodes that come off of the negative side, which go, this one has 3 diodes, here, here, and here. You can see the 3 pins there. This one only has 2, these 2 diodes right here. But if we check those diodes, let me get this all in shot. So first I'm going to check the extra one here that the F revision doesn't have. There's 1.2 volts that way, and 0.2 volts that way, so that looks like a germanium diode. Kind of interesting that they would still be using those in 71. Let's check these other diodes here. So yeah, that's a dead short, and that's a dead short. And just to make sure that there's not something else in the circuitry throwing it off, if we check those same diodes on this machine, we get 0.5 that way, 0.5 that way, so those are silicon, and 2.2, 2.2. So yeah, so I don't know if there's anything significantly different that would cause the diodes here to show, you know, what you'd expect for a diode, and versus here to show dead short in both directions. So I think it's actually those diodes are the issue. And unfortunately, to get at those, I am going to have to desolder the keyboard because they're just so buried down in there. I can try and see if maybe if I can clip them just to make sure that the short goes away. But to replace them, if that takes away the short end, to replace them, it's definitely going to have to desolder that because there's no way I can get in there. So yeah, and this guy actually, if you check him, let's go back to Ohm's mode here, and we check our first suspect. You can see it's charging up. I might have the cloudy reversed. No, I don't. That's like cloudy. But you can see it's charging up. 1.4 megohm is definitely not shorted, so that wasn't the issue. So yeah, let me see if I can investigate those diodes further. Oh, that didn't work. I don't know how they put these in there, but melting the solder on here didn't actually seem to release the pins. So actually what happening was I was trying to melt the solder here and then try and pry up to, you know, lift the pin and kind of work my way across, but all that was happening was it was lifting the traces off of here. So rather than fight with it, I decided to just took it off, and when I put it back together, I'll just run jumper wires, you know, to replace these traces. I'll probably use a real thin wire that'll fit through this hole, so I can run a jumper wire from wherever the trace starts up and then loop it around that hole and then bring it down to the board. And we'll just have to do that. I have no idea how you're supposed to get that off, because you can't desolder from here because the solder is on the bottom of the traces, so you can't get a soldering iron in each of those to desolder. So I have no idea. Anyway, I clipped the first diode here, and that seems to be the bad one, because now if I check the other diode, which was testing bad, is now measuring 1.5 that way, and 2.2, that doesn't seem right. This is some kind of, this is a Xeno diode or something. I don't think so. So it's measuring 1.5 that way. 2.2 that way. So I'm not sure what the deal is with that. Either way, it's not shorted. So I'll have to check that. So I'm going to do is, at least we should be able to at least turn this on without the keyboard connected. And actually we can, bridge some of the pins here to simulate key switch if we want to. But for now, I'm going to, just for testing, I'm going to remove the diode from this one, pop it in there, and see what we get. Alright, so I ended up replacing both of those diodes. The first one was definitely shorted. The second one, it measured kind of funny, if you remember, like it was measuring 1.5 one way and like 1.2 the other way or something weird. And when I tried to pull it, I ended up just breaking it in half, so unfortunately we can't test it now. Can't even see it because the camera won't focus. So I just pulled the two diodes off this board and put them in there. They are 1N4148, I think it was. Let's see if you can. It says on it. Well, no, maybe. On. Yeah. So the first line says 1N4, and the bottom line says 148. So 1N4148, right? 1N4148. Both of them are the same. Because I don't know why this one has an extra diode here, which is not present on this one. You can see it's not populated there. I don't know. Anyway, so these were both 1N4148, I think it was. I keep getting the number mixed up for some reason. So I pulled two of the same thing off here and stuck them in there. Also, I tried powering up with this questionable diode in, and it didn't work, but I forgot to put the tantalum capacitor back in. So it could have been working because there was no filter in there. I don't know. Anyway, both of them are replaced. Capacitor's back in. Now if we turn it on, you'll see we get a nice stable 0, which is good. I think you can see that. Now you can see it, maybe. There are some ghosting L's there. I'm thinking that might be like interference because of this messed upness. But I wish that would show up better. It really is hard to see. But what we can do now is, the way that the keyboard input works is it shorts a control pin on the chip to a digit driver line. And it just so happens that the control pin for digit entry and the first digit are right across from each other. So if we just jump around the third pin on each side, which if you can see, but we have now entered a bunch of ones in there. I don't know what the other pins are. Actually, let me go and check that real quick. I'm not sure how this is going to show up, but the third pin is the digit control. So you say enter 2, that enters 2. And then the pin next to that, the fourth pin on this side, is the operation control. And if we short that to the fifth digit driver, which these are all in order, so that's the fourth pin to the 1, 2, 3, 4, 5. That should be a plus. And then we'll just do, I just added a bunch of 3s in because no debalance control. If we add that in, so now we want to do, again, pin 4 here. 1, 2, 3, 4, 5. I think that's right. 3, 3, 3. It's like a 5. I think the display is kind of messed up because I think we're getting some interference from this. So I think it's working. We should have entered 3 3s plus 2, and it looks right, but like I said, there's a little bit of ghosting on the display. I think that's just because of this interference. So it looks like it's 3 3 5. which would be correct. Hopefully that'll work. So, yeah, I'm going to, you see somebody already put a little barbed wire in there. So I like to jump over a little torn trace there. So yeah, I'm going to come up with a solution for this. Like I said, I think it's going to take some real thin wire and follow the traces up and then loop it around the hole so that all of the wire strands will stick down, and then I can poke them through there. I think there are a couple of traces that I've lifted, so I'll have to try and fix that as I go. But one of the advantages will be if the wire I use is not as rigid as these pins, I should be able to manipulate the keyboard easier if I have to kind of play around with getting some lifted traces soldered back down. So, yeah, like I said, I don't know how you're supposed to do that, but I think we will come out of it okay, hopefully. So yeah, let me figure out how I'm going to put all this stuff back together, and hopefully then we'll have a working Bowmar901b. Okay, so I think I've got everything connected where it needs to be. No, it's not pretty, and yes, a diode appeared there. We'll discuss that in a minute. However, if I put that together like that, oops, there's the button. You'll see that it does turn on. But now it's going to hit an error because it ran out of space. I just pushed the key all the way, that's why. See, now it works just fine. That works. That's some point and zero work. CE works. Minus works. Times works. Now, if we let it set, let's enter some numbers. And if we let it set for a little bit, what's going to happen is the display is going to time out. And that's what this D key is for. So just let it, hope you can see that, by the way. It's showing up on the camera. Just let it sit here for a minute or so. So yeah, we're all waiting for that timeout. There it goes. So now it's kind of hard to see, but in the middle appears a little dash right there. So you know that the machine is on, but the display has timed out. If you push the D key, it comes right back on. Now, what I've discovered in my reverse engineering adventure, which I did for two reasons. One, because I wanted to actually have some, useful content in this video instead of this hack slash that we have here. And also because I needed to. You'll notice that we were getting the ghosting, before we were getting the ghosting L's in there. That's no longer happening. That was actually due to a diode here, which is this diode, which had actually shorted. And so that's why I just popped one on the top here. This one, of course, was on the other side, but since I'd already started working on this before I went in to diagnose that, because initially I think I mentioned this before, that I thought it was because these were all, disconnected, that there was some kind of interference or something that was causing those ghosting L's. That was not the case. The L and the dash are actually not controlled by the main processor chip. They are controlled by all of this extra stuff down here. And I'll go into this in a little bit detail in a little bit because I have reverse engineered this. But basically this transistor turns off all of the display driver chips. So these are the digit drivers, these are the segment drivers. So this is a multiplex display, obviously. So each of these will get a signal on one of the pins, one pin at a time for each digit, and then these will get, at the same time, these will get the segments for that digit. So for example, if you have like 1, 2, 3, it'll start by driving digit 1, which will activate one pin on one of these chips, and then that will connect the output pin, which was up to the, I think there's a common cathode, LEDs, yeah, there's a common cathode. So you'll get a signal on digit 1, which comes out of this chip, that's digit 1, I believe that's that pin right there, which is connected to one of the pins going to the keyboard and one of the inputs on these digit driver chips. When you get a signal on digit 1, I've written down which pin it is, but I have to go back and check my notes. Anyway, you get a signal on digit 1 that will tell one of these chips to pull digit 1 output low to ground, activating digit 1 in the display. At the same time, I think so we had 1, 2, 3 on the display, right? At the same time, the correct segments for 3, which would be the bottom one, the two side ones, the middle one, and the top one, will get activated via these chips. So the segment pins come out this side. It will send, I think that's what, 5 segments. So 5 of the segment pins will go high, which will put voltage, driving voltage, out of 5 outputs on these, which go up to those 5 segments to light them up. So it's double action. You got the segment drive connecting the segments to positive. At the same time, the digit drive is connecting the common cathode digit to negative, and so the current can flow through. Now these chips get their driving voltage through this transistor. So if this transistor turns off, these chips have nothing to provide to the display, so the display goes out. So you may ask yourself, well, where does that little dash come from then? Well, that's also controlled by one of these, I forget which one it is, but one of these transistors then actually directly connects that segment to positive voltage when digit 5 line goes high. So this circuitry, which again, sorry, I'll show that schematic in a minute. I just have to clean it up a little bit because it's kind of messy right now and you won't be able to really read it. But basically, this circuitry listens for digit 11 and digit 5. So when the display times out, when it sees digit 5 and it's in display timeout mode, it directly drives that dash segment. Digit 11 is for the L. So if it detects a low battery and it sees digit 11, it will light up the correct segments for the L. That's what these diodes here are for. These diodes, which one of them I've stolen as parts for the other one, but there were 3 diodes here. Those connect directly to the anodes for the 3 segments to make the L. Those are activated by this pair of transistors here. This transistor here is the display timeout. It's got this 3.3 megohm and this, what's that, 6.8 microfarad capacitor as an RC time constant circuit. So that's tied in with these diodes up here. These are connected to the the 2 inputs to the chip, which listen for key presses. So if you remember, one of these outputs listens for a digit drive to be connected to it to register a key press for a digit key, and the other one listens for one of the digit lines to be connected to it to detect a control key. And then those 2 lines go through these diodes. In addition to this third diode is for the D key. So this line will get a pulse on it through these diodes anytime a digit key, a control key, or the D key is pressed. That goes down to this transistor and turns it on. So anytime a key is pressed, this transistor turns on and dumps this capacitor to ground. So that prevents the display from timing out while you're actively using it. And when you don't use it for a while, this cap has time to charge up. And when it does, then it puts it into display shutdown mode. So that's what some of these transistors here are for. These 2 and these 2 are the clock oscillator, and these 2, I think it's just these 2, as far as I can tell, are driving the transformer here for the power supply. And actually I was wrong. I thought that this developed all the voltages necessary, but it's actually not the case. Ground, as you can see right there, ground is connected right to battery negative. This is the battery negative line going in here, so you can see it goes right to that same around the board ground plane. So ground is connected directly to the chip, and actually battery positive is connected directly to this pin on the chip. So the only voltage that they actually generate is the negative voltage, which goes into this pin down here. So you've got positive 7 volts ground and negative 7 volts. So yeah, when I first looked at this, I thought that all this stuff was to generate multiple voltages, but it's actually not. It's just generating the one. And then all this other stuff is for extras. Well, I mean, the clock, obviously you need that, but all this other stuff down here is for the extra stuff, like the display timeout and the low battery detection. So yeah, an interesting thing you'll notice that there's nothing here on this board, but this board had a diode on it. Why? I don't know. And again, I'm not quite sure why that shorting caused those ghosting L's. It must have messed with the gate voltage on the transistor that drives those segments and caused it to always be somewhat turned on, I guess. But anyway, so far it seems to be working. And you can see when I show this, I did a test fit before. Let me clarify that. When I showed this, I put this together because I did a test fit before and it didn't hit anything, like the little bit of protrusion which we now have. You can see I arched some of those connections to jump over other connections. Seems to be fine. I think it should go back together just fine. So, a bit of a note on this. Obviously, this is not the correct way to do this. And this is part of the reason why I don't take customer repairs. Because if someone has sent something into me and I fix it like this, that's obviously not going to go. So this is my own thing. So as long as it works and is reliable, I'm going to be happy with it. I don't care that it looks like this on the inside. The correct way to fix this, honestly, if you get one of these and it has that problem with some of the diodes shorted, I would say just, push them out the front, like you can just heat up these pads on the back and use like a little wire or something to push them through, and then just solder a new one on the back like I've done here is what I would do. I didn't realize that trying to get the keyboard off would cause such a mess. I honestly think that the pins are actually crimped into the through holes here somehow, because even once I pulled the keyboard off and I had just the pins here, heating them up to melt the solder, it would melt the solder, but they still wouldn't release from the board. So I don't know what the deal is there. Obviously, you're not supposed to take that keyboard off. And if you try to melt the solder on the bottom of the keyboard, like the keyboard would be here, you try to melt the solder on the bottom of the keyboard to try and lift the keyboard off the pins, you'd end up just melting these chips, I think. There's not enough room. So you can see how close. Actually, the pins are just about the same height as those chips. Now, of course, these pins might be a little bit higher because these ones go into sockets while the other ones went through the board. But even so, that board is like right down on here. There's really no space to get in there with a soldering iron. So honestly, I think you're just not supposed to take that off ever. So yeah, that's why I don't do custom repairs, because that allows me to do stuff like this, which, although it is not the correct repair, does seem to be working. But like I said, obviously not acceptable to do that to somebody else's thing. You can only do that to your own thing. So yeah, something else that I probably should have mentioned before, but I kind of wanted to get this back together to make sure it's going to work. But the display between this version and that version is different. That one, and you can go back and check the beginning of the video when I had them both out laying here, that one has individual packages for each digit, while this one just has, come on, the LED chips directly planted on this circuit board, and they just stuck this red filter on the front of it. I'm a little bit curious to see what they look like without that red filter. Another thing you'll notice, these do not have any magnification in front of them. If you look at that, those are the actual full-size LED chips stuck on the board right there. These are not the later version displays where they have a little teeny tiny magnifying glass on top of each of the chips. These are actually full-size LED digits. The reason for the change, I don't know. You can see Bowmar actually made these boards. I think Bowmar came up with these LED displays first, and then I guess didn't know what to do with them. They started to make a calculator, I believe is what happened. So Bowmar was a display manufacturer, and I believe they supplied other companies too with their displays. Now whether they also made the ones with the magnifying glasses in front, that I don't know. Yeah, so my guess as to why they would have changed is power consumption. These early nickel cadmium batteries, obviously not, these aren't the early ones, but the ones that would have been in here when it launched, did not have anywhere near the capacity that we have now. And these LED displays obviously are not anywhere near as efficient as what we get LED displays now. And now, right now, LED displays are, highest efficiency that you can generally get. This is not really true. OLEDs take more energy than LCDs, but anyway, generally today LEDs are thought of as high efficiency, but in the 1970s when these things came out, these were actually pretty power-hungry displays compared to stuff like LCD when LCD came on the market. Obviously, this would be better than like a NICSI or a VFD. For one thing, the size, and you don't need the higher voltages that those things need. And it's probably somewhat more efficient too. But once LCD displays came on the market, those were so much more efficient than LEDs. And when Sharp introduced their first handheld LCD calculator, that only had one AA battery. Let's see, does this have a power rating on it? Because that would be a good comparison. Full charge in 14 hours. I don't see anything here about a power rating. So that's the Craig label. Let's check this one. Yeah, I don't happen to see anything here. Let me check the book. I have the manual first. Let me check if the manual says anything. I'm not going to find anything in the manual about the power consumption, but I did find that on the back of this, HP35, it says 500 milliwatts. Now, of course, this has the LED display. See if it'll turn on. No. Yeah, the battery never... There it goes. Battery doesn't make good contacts, and then you have to squeeze it. I'll have to fix that sometime. So this has the LED displays with magnification. So you can really see the little magnifier bubbles in there. That's 500 milliwatts. Look at this one. This is the LCD. That's 20 milliwatts. So quite a difference there. And of course, that's why these use rechargeable batteries, because they draw so much current. You're draining the batteries all the time, so better to use rechargeable ones and keep throwing out, replacing the batteries all the time. But this one, because it uses so little, they just have one not rechargeable battery in there, and this battery lasts for a long, long time. I can put it back together anyway. There it goes. This is the LCD. I really like these early style LCDs. They're nice, solid silver color. Focus on that maybe. So yeah, that's my theory anyway, why they went to the magnifying ones, because it made them smaller, so then they would use less power, is my best guess anyway. I think these Bowmar ones are the only handheld ones I've come across that use the unmagnified LEDs. Anything else I've come across uses the magnified ones, but yeah, anyway, this is actually pretty cool. The entire circuit board in here is just one solid piece of glass for the LCD space. So the display is actually in the board, if you want to call it a board, and they just ran the glass all the way down through the traces on it, but that's not the point of this video. So yeah, something else that I wanted to mention, you'll notice that extra wire that I had sticking out here I took off, and the reason is because once I figured out how all the circuitry worked, I realized that was never going to work right where I had it. What I did was I connected that wire to battery positive, thinking I was using that as a battery sense line, but that's actually not the case. The way that I had it set up, feeding battery positive into where I was feeding it, it would mean that the calculator would never go into the display off mode. I should say the display sleep mode. Because basically that's that same trace that is listening for the key presses, So basically feeding battery positive in there, you're holding that transistor on all the time, and then that cap is never going to charge up and it's never going to time out the display. So I took that out. I don't know where it's supposed to go. On this earlier version, that trace, which is this trace right here, you can see they have the through hole for it there, but no wire was populated. That trace actually runs all the way up. You can see there's those 3 diodes where they connect. What's the focus doing here? And then it runs, you can see it goes through the plated through hole there with that diode, and then runs up on the other side, all the way up around under the display, where it connects to a diode, you can see there. And that diode connects to this white wire, which was connected to the AC power supply input. You can see on the back here, that white wire relating to the AC power supply. So my thought is, the idea there is whenever you have the AC power supply plugged in, that's going to be feeding 60 hertz pulses, because it's halfway rectified from the AC power supply. Going to be feeding 60 hertz pulses onto that line, and my best guess is that is so that the display will never time out when you have the charger plugged in. Is, as far as I can tell, the reason behind that. If that doesn't work on this machine, that's no big loss. I don't really care. I tried looking up some pictures of where that wire went on other machines. I'm calling it a machine. I don't know if you really want to call this a machine, but I'm so used to working on the mechanical calculators. But anyway, some other models of this to see where that wire went. The only thing I could find was a revision C, and that revision C actually had 4 wires coming out and going over here, and I couldn't really tell where all of them went. It did have, you can see there's actually a hole there. That revision C had another post in that hole with a diode connected to that. So, yeah, it could be possible that there's supposed to be 2 diodes over here, and then have a setup just like the revision F has it, where one is the main rectifier diode that charges the battery, and then the other one is just that that low current diode to put the 60 hertz pulses on that sense line to keep the display on. But there's nowhere here for that diode to go. There's not enough posts. So I don't know. Like I said, I didn't replace the batteries in here. That was done before I got this. So was there another post here that somehow got lost during that? Or yeah, I really have no idea what the deal is there. But as far as I can tell, that's all. The only purpose of that is to keep the display on all the time when the calculator's on and the charger's plugged in. Obviously, it's not going to turn it on when the calculator's off, but yeah, I think that's the only thing that I can tell that would do is keep the display from sleeping when you've got the charger plugged in. So I'm not going to worry about it too much. Like I said, everything seems to be working. We no longer have those ghosting L's. The display timeout does work. So yeah, I think as far as repair here, I think I'm going to be satisfied with that. I mean, obviously I'm not proud of this, but you know, it does work, so I'm going to go with it. I said if I had to do it again, I would just leave the keyboard and the circuit board together and just push those diodes out from the front and then solder them on the back. And I think that's the best way that I could hope to do it, because I really don't see a feasible way to separate the keyboard without making a mess like this. So anyway, yeah, after this we'll take a look at the schematics that I drew up, which are not very pretty, but it hopefully should at least be somewhat readable, and see why we've got 5,000 transistors in here. I think it's 5,000, and we still need all these extra transistors down here. Alright, so we'll start out by taking a look at this. Down at that calculator museum, they have this nice page about the TMS0102 family. The actual chip in here is a TMS0103, but as far as I can tell, the pinout and the operation are basically the same. You know, maybe it has a little bit extra memory or something for the microcontroller, but So yeah, see here's the whole different family here. They go with 0101, 0102, 0103. That's a calculator right there, Bowmar901b, and so on. So I guess all these chips are, the pinout and operation is pretty much the same, just minor variation, I guess. Anyway, so they have this nice pinout here, so you can see clock chip, KP, and all the digit chips, VDD, VGG, and these are all the segment outputs, and then DP for the decimal point segment, and then the inputs for KO, Canon, and KQ, and then VSS, which is the positive 7 volts. And of course, they have their little voltage chart here. This is what I was going by. They have VSS at 0. Why is focus so messed up? They have VSS at 0. I've been calling that 7, and then VDD 0, and then VGG negative 7. They just changed the reference point, so it's the same difference really. Just semantics. Voltage is always relative. So yeah, they have a little description of the chips here, and then which segment maps to which segment on the actual display. And then down here they have the input map. So basically the way that the chip works is these outputs are always scanning, so it'll pulse D1, then D2, then D3. At the same time, it has the correct segments driven to display for that digit. So like if it has, say, a 3 in digit 1, when D1 is pulsed, the correct segments will be also driven high to light up the segments with the 3, and then the segments will change when it pulses the 2, and so on. And then at the same time, it's listening on these input pins here and KP. Focus is not working. Anyway, it's listening on those input pins to see if the digit pulse appears on any of those input pins via this chart. So like if you push the 1 key, it will connect D1 to KN, that triggers a 1. So if the microcontroller sees a pulse on KN at the same time it's driving D1, it knows that the 1 key was pressed. And then similarly for KO, if it sees a pulse on KO at the same time it's driving D2, it knows that the multiply key was pressed. And then so on according to this chart. And then KQ looks like it's just listening for the constant key. So in addition to providing this nice page, they also provide a page here for the segment driver chip. So you can see the pin out there. And also for the digit driver chip, 75492, which you can see the pin out there. So yeah, I'll try to remember to leave links to these down in the description if you want to take a look at that. Also, I've gone through and looked at some of this. So this is kind of a mess. Obviously, I'll just kind of map out which digit line connects to which chip. If you really want to know, you can try and decipher this. I don't think that's really that important. The interesting part to me was the transistor circuitry, but anyway, that is there. And this up here at the top is the pinout for the keyboard connector. So like pin 1 is D4, pin 1 is D1, pin 2 is D4, pin 3 is D7, and so on. Pin 8 is a special one. We'll talk about that later. And then, yeah, that's all the pins on the keyboard connector. So you can also take a look at, we'll go on to the negative power supply here. So this power supply is these two transistors right here, right directly under the coil. So that's these two transistors here. Now, a note about the transistors. These transistors don't have any part numbers on them. If you look closely at the front, there's a wire in the way. You can see they have the emitter, base, and collector labeled. Come on, I almost worked for a minute. No, it's not going to show it. Anyway, they have the emitter, base, and collector labeled on the front of the transistor, but there's no part number. That's all that's there. And then on the back, you see the back of that one, they have color codes and then a color code on the top. What the color codes mean, I don't know. If you try and search for transistor color codes, all that comes up is resistor color codes, which is not very helpful. I tried guessing that maybe they represent just, numbers like the resistors do. So for example, that one's green, orange, orange. So that would be 533, or in reverse 335. Or if we take into account the top, which is green, be 5335 both directions. But searching for those numbers didn't really seem to provide anything coherent. So I don't know what these transistors are. And I've just taken a guess whether they're NPN or PNP based on their operation in the circuit. These I may have got backwards. I did not take out the coil, and this box here is the coil, by the way. I did not take out the coil and determine which pins are connected to what. So I don't exactly know what the internal connections of the coil are, but I did go through and look at the external connections. So what I'm getting at is I've drawn these as PNP, but they may actually be NPN. I'm not quite sure on these ones. On the other, some of the other ones I'm more sure, but these ones I'm not so sure. Anyway, so yeah, the battery positive comes in, goes into the coil. I don't really know what to say here because, like I said, I didn't bring out the internal connections here, but you got two driver transistors. The bases are connected by 1 nanofarad capacitor. You've also got some filtering over here. So this is the positive and the negative or ground. So this would be the battery voltage right across here. They've got a filter capacitor there. They got a resistor with a capacitor going into the coil. So yeah, how that works, I don't know, but that's the topology of the circuit. And then of course you've got the output here, negative 7 volts, with 2 diodes coming off the coil. And there's this random diode here. Now this diode is present in the revision E calculator, but is not present in the revision F calculator, but I've drawn it here anyway. And then that pin is also connected to ground. So yeah, for whatever that's worth, that's what it is. Moving on. This is, if you really want to take a look at this, this is the segment outputs and where they connect to the segment driver chips. Again, that's kind of a mess. I didn't clean that one up because it's not what my most interest was here. And then up at the top here, I've pinned out the display connector. So that would be these pins right here. I've only labeled the segment ones because the segment ones are the even ones, the odd ones are the digit ones, and the digit ones go in order. So for example, pin 1 is digit driver 1, pin 3 is digit driver 2, pin 5 is digit driver 3, and so on, all the way up to, this would be digit driver 8, and this would be digit driver 11. It has 11 total drivers, but this is only an 8-digit display plus the error low battery digit. So this is the most significant actual result digit, so digit 8, and this is the error or low battery digit, so that's digit 11 always. And then this is the two segment driver chips. So you can see like pin 2 is segment C, which is also the third output on the upper chip. Again, if that is worth anything to you, it's there. You can pause the video and look at it if you want. This is a mess. I've cleaned this up on another page. This is the clock circuit, 4 transistors. That is this one, this one, this one, and this one. So it looks to me like this is the actual oscillator portion here, because you've got positive 7 volts coming in and going down. There are a 12K resistor to the collector here, 12K resistor to the collector here, and then they've got some feedback from the collector of this transistor to the base of that one, and then vice versa to a capacitor. And then looks like then that goes to the base of this, which then goes up to the base of that to drive that. So what the point of this diode is, I'm not exactly sure. maybe that's, yeah, I'm not exactly sure. My guess maybe to like, you know, for some waveform cleanup perhaps, make it more square, I don't know. Anyway, so yeah, it looks like this would be the oscillator section, and this would be the output driver section of the clock circuit. Again, not super interesting, just, you know, an oscillator to drive the clock. This is where things get interesting. So this on the top here is the display timeout circuit. So this is composed of this transistor, this transistor, this transistor, this transistor, and this transistor. And I've labeled them, so this B is the blue one over here, this DG is the dark green one here, the red one here, the white one here, and the green one here, just to kind of correlate those. So, let's see if we can walk through this. Start at the beginnings, I guess. So into the base of the blue transistor, we have a 100K resistor, which is connected to 3 diodes. In some designs, 4 diodes. We'll get to that in a minute. For now, just look at these 3 diodes, and this 100K resistor to negative 7 volts. The other side of these diodes are connected to the D pin, which is actually turned out to be this question mark here. On pin 8, that diode is this diode here. So pin 8, or I should have labeled that as an 8, but I labeled it as a D because that's the D key. Pin 8 connects to the D key on the keyboard, and that input feeds into this diode. KN feeds into this diode, and KO feeds into this diode. And I've also labeled that KN is pin 26 on the TMS 103, and KO is pin 25 there. So those 3 diodes all feed into here, which goes to the 100K resistor into the base of this transistor. The emitter is going to ground, so that's pretty obvious. This is a NPN. The collector goes up to a capacitor to ground and a 3.3 mega ohm resistor to positive 7 volts. So this right here forms the time constant, where this resistor will slowly charge up this capacitor when this transistor is off. Anytime the D key or a number key or a operation key is pressed, that will send a pulse through one of these diodes onto the base of this transistor to turn it on, and when this turns on, it will dump this cap right to ground. And that will basically reset the timer. So when no keys are pressed, it's in timer mode, charging up this capacitor, and as soon as the key is pressed, it shorts out the capacitor and basically resets the timer. Now, once this capacitor charges up, it will send a signal. Well, I mean, the signal is always there, but once this reaches a significant voltage, to turn on this transistor, you can see this transistor has a, I'm not sure why they had this little voltage divider here, but they got a 10K to the emitter and then a 6.8K to ground, so some kind of voltage divider. They want some specific voltage there for some reason. Maybe to do with setting the turn on voltage here, because the way that these transistors work, this is a PNP by the way, in order for the transistor to turn on, current has to flow from the emitter to the base. So I wonder if I have that backwards. Not sure. Anyway, I'm not sure if I have that backwards or not. But anyway, the idea is that this line will be low as this capacitor charges up, and when it gets to a certain point. So yeah, I must have something backwards there, but the flow is correct. Not sure about that. Anyway, and this might be an NPN then. Maybe I have that backwards. If it was an NPN, then this would have to reach a certain voltage to turn it on. If it's a PNP, then a low voltage would turn it on. So I think I have this backwards. This must be an NPN. And then when this raises to a certain voltage, I think that would make sense. Yeah, I think this must be an NPN, so I think I have that backwards. So anyway, the idea is that when this raises to a certain voltage, it will turn this transistor on, which will then go down here, and then this one for sure is a PNP because the emitter is connected directly to positive 7 volts, so it has to be. So yeah, for that to work, that makes sense. This is an NPN. This would be biased towards low because the resistor divider would have a somewhat, since this resistor is higher than this one, this would be lower than half of 7. So if this turns on, it would pull this to lower than half of 7. So yeah, so it would pull this low with respect to this out. So yeah, this must be an NPN. And then when this voltage raises to a certain amount, and yeah, so that would make sense. That would make a lot of sense. If this is an NPN, then when this voltage raises to the point where current can flow from the base to the emitter, that will turn the transistor on. So yeah, that's why they've done this here. This sets the turn-on point for this transistor based on the emitter voltage. So this emitter voltage is fixed, relatively speaking. It will change somewhat when the transistor turns on and current starts flowing, but the idea is this voltage is fixed. So when this base voltage rises, 0.5 to 0.7 volts above the emitter voltage, current will flow from the base to the emitter and turn the transistor on. So that sets what voltage this cap has to be at to turn this transistor on. And then when that turns on, it will pull this line down, which will allow current to flow from the emitter to the base and turn this transistor on. And then when this transistor turns on, there'll probably be minimal drop across it, which will put voltage on this line, which goes through a 150 ohm resistor to the collector of this transistor. And so basically the idea being there is effectively this will have, power supply at the collector. Now, in order for that power to be passed on, the base has to be have current on it, or voltage on it rather, current and voltage, but the base is connected to D5. So when a pulse comes from D5, that will turn this transistor on, and D5, if you remember, is the digit right in the middle that gets that little line in the middle to indicate display timeout. So basically, what this is doing is, at the timeout time, it will turn on power to this transistor, and this transistor will only turn on when it sees a signal from D5. So, and then the output of this goes directly to the display. So basically, in display timeout, the circuitry is listening for digit 5 to be active, and when digit 5 is active, it drives the middle segment directly. It does not use the segment driver chips. The circuitry is directly connected right to the display anode and injects current directly into the display. Now simultaneously, see, there is another voltage divider over here connected to the base of this transistor. So from when you get, normally this would be pulled down low, and since this is a PNP, when this base is pulled low, the transistor turns on, and when it turns on, it sends out power to the segment driver chips. Now, when this collector gets pulled high, because there's a voltage divider here, it will pull this base high, which will turn this transistor off, and turn off the segment driver chips. So basically, the way that this works is, when this cap charges up, because there's no keys being pressed, it will turn off the display drivers, and it will turn on the middle segment only when digit 5 is being activated. So that's how they time the display out and how they draw just that one line on that middle digit. So yeah, that was the interesting part. And the other interesting part is the low battery indicator, which I've drawn down here. And that, I'm thinking this is the battery sense circuitry. I don't exactly know how it works because I don't know what kind of diodes these are. I'm thinking they must be some kind of xeno diodes. Yeah, I'm thinking they must have some kind of xenodiodes, so that when the battery voltage gets, low enough, it will pull this base. How to pull it high, somehow. Not sure. Yeah, I'm not 100% sure exactly how this is working because, like I said, I don't know what kind of diodes those are. But anyway, so this has this diode resistor circuit here on the base, and also an input from D11 on the chip through a 100 key resistor to the base. So when this base goes high, and again, this for sure is a NPN because the emitter goes right to ground, so it has to be. And there's no negative voltage in the circuit, so it has to be a NPN. So when this transistor gets turned on, it will pull this base low, which will turn this transistor on. And again, this isn't a PNP, and it has to be because the emitter goes right to positive 7 volts, so this has to be a PNP. So when this goes low, this will turn on, and when this turns on, it will put out current through this 47 ohm resistor to these 3 diodes here, and these 3 diodes directly connect to the 3 segments needed to draw the L. So basically, if the battery is low and digit 11 is being driven, then it turns on the 3 segments and draws that L in digit 11. So yeah, I hope that makes sense. And that's why they have all these transistors. When I first looked at this, I thought all this was just for, generating, a bunch of different voltages for this chip. But it turns out that it's only these 2 transistors generating 1 negative voltage, and everything else is where you got the oscillator here, and you've got the low battery here. That's just these 2 transistors, this guy and this guy. And then all these other things across the bottom are for the display timeout. So yeah, quite a lot more going on than I initially suspected at first. I hope that kind of makes sense how things are working there. Like I said, not too sure exactly how this is detecting low battery. These must be some kind of xenodiodes or something that get unbalanced when the voltage gets too low or something. I don't really know, but that is how it's wired up. So yeah. And something else I wanted to mention. All of these chips here. So the way that these chips are is they have a collector input for each individual digit, and I'm guessing so you can resistor limit each LED individually, which is what they've done here. So each LED segment gets its own individual 150 ohm resistor, which are all these guys here. So these chips, for every digit, or every segment rather, they have an input, an output, and the collector. So the collector is connected to these resistors, and then these resistors go directly to positive 7 volts. So I'm thinking that's so, if they only had 1 pin for VCC, if this chip was driving, say, all the segments that it was connected to, that would be consuming a lot more current than if it's only driving 1. And of course, you have to have these resistors for current limiting on the LEDs. So I'm thinking that's why they did that. They have a separate collector for each LED segment, which then allows you to have a separate resistor for each LED segment, so you can get constant current through the LEDs. Anyway, so yeah, each of those chips has a 150 ohm resistor to the LED segment, and if you look here, they're doing the same thing. Since this emitter directly connects to an LED segment, they put a 150 ohm resistor on the collector there, so that's current limiting for that segment. And when they were driving 3 segments in parallel, they used a 47 ohm resistor, which is as close as you can get to 1/3 of that. So that's how they're keeping the current constant for all the LED segments. Now, I was thinking of that though, I suppose there might be a slight issue in the time that the low battery indicator and the error indicator are on at the same time, because that would have the segments driving the E, 3 of those segments are also used for the L. So if you got an error on the display and low battery, you'd actually be double driving those segments. It's kind of interesting. I haven't really thought about that. And I don't really see anything in this circuit that would prevent it. That's kind of interesting, actually. Yeah, I'm thinking that would be the case. And have this 47 ohm resistor providing current to those 3 segments at the same time as the 3 150 ohm resistors on the collectors for those segments are also providing current. So, yeah, it's kind of interesting, actually. I don't know if that would do any damage or not, but I'd imagine at least make it much brighter. I wonder if that was their intent. So you kind of have like an L superimposed over the E. I don't know. Anyway, I don't intend to try it just in case it would fry the display, but I don't know what the maximum current is on those LED chips. But anyway, I hope this made some sense. Definitely more going on here than I thought. So we're just to round this video out. Take a look at the rundown technology here. In my opinion, I think that the advent of the registerized and then eventually the handheld programmable calculator, it's kind of one of the, as you could say, most striking demonstrations of technological evolution in such a short period of time. This calculator came out in 1973. So think about that. This was less than 10 years since the very first transistor calculator was on the market in 1964. So it took 9 years for them to get from, the huge, Frieden EC130, which costs as much as a car, down to this handheld thing. And then in the next year, HP released the programmable one. So basically, you went from, this huge 50-pound desktop monster down to a programmable thing in your hand in 10 years. And think about, compare that to today. If you look at, the phones and stuff that are on the market today, obviously they're better than what we had 10 years ago, but, it's not like there were no smartphones or no handheld devices 10 years ago, which is kind of the case here. The only handheld electronics really 10 years before this were just radios. There was no handheld calculators. There's no handheld electronic calculators in 1964, and there wouldn't be until 1970. So, even this is what, just 3 years here, 1970, 71, 72, 73. Quite a striking difference for a short period of time. I mean, the difference between, your phone today and your phone 4 years ago, in my opinion, is not this much of a significant difference. But anyway, I think these machines are cool. This, of course, is the Sharp EL8. So one of the first handheld calculators, and yes, it does technically fit in the hand. Turn it on here, clear it out. It has the lovely Itron tubes. See the stylized display there. I think the 6 is especially weird looking. And of course it has a error dot up there and a negative indicator. So if we do something like, see, the negative lights up there. And then this arrow, and there's also the arrow little dot up there lights up. Let's see if we make the arrow light up. There it goes. So the arrow dot lights up there. And then also for low battery. And then funny thing is on this one, the switch on the side has off, AC, and DC. So I don't know why they did that, but the on and off batteries, you switch to DC. turn off the charger, you turn it on AC. So if I turn on the AC now, that's going to happen because I don't have the charger plugged in. But if you plug it in and then turn it on DC, then the alarm lights up to let you know that you dummy, you're trying to charge it and then you're running it off the batteries. Why they did it that way, I don't know, but that's the way it is. Pretty cool machine. And then of course 1971, and I think this they call one of the first handheld calculators. I think this they call one of the first pocket calculators. This will not fit in my pocket. This would. This is the one we just fixed, the Bowmar901b. It's kind of hard to see it. Display's not super bright, really. Well, because I do have pretty bright lights here. And then, of course, 1972, the first scientific handheld calculator by HP 35. If I can hold the batteries. Is the way that these batteries go in here. This is a reproduction pack. I think this might have came with it, or came with one of the ones I got. I just got these little spring things here. So these reproduction ones are not quite as big as the original ones. They kind of flop around in there and don't always make good contact. And I put this in, there's still a little bit of, oh no, it seems a lot better. See if it works now. Yeah, it does. There you go. This has the magnified one, so off-angle viewing is, well, it's not as bad as I thought it would be. Of course it has, 80x, going degrees. Yeah, and there's my batteries not making a connection. So this one, all the decimal points light up for bad batteries. Yep, so in degrees. I think this only does degrees. So that's square root. I think it does x to the y. So x is the lowest register on the stack. So we're going to do 5 square, we have to do 5, enter 2 x to the y. No, apparently not. I don't know what happened there. Maybe my batteries made bad connection. No, I did it wrong, right? Hold on. X to the y, so yeah, I did it wrong. That would be 2, enter 5, power. That looks better. It's a bit of a floating point error there, but we'll ignore that. Of course, the HP 45, 1973, basically just an enhanced version of the 35. Added a bunch from registers. This only had 4 registers on the stack. This had the 4 register stack plus you can store into one of 10 registers. So you press, and I forget which one it is. I think it's this one. No, is that stack rotate? I don't know. It might be this one. The R. You know what? It says it right on the back. And I have the instruction book somewhere too. Register arithmetic. Store xn. Stores x something n into register n unchanged. You call. So it's just STO. Not sure what the x is. Anyway. This one, the batteries are, or maybe the batteries died. Again, it's a rebuilt pack. I should probably rebuild one that will fit properly, but maybe we'll do that someday. See if this will. Yeah, it might be dead. Nice thing is, we can just do this. That seems pretty loose too. Actually, that's going to work either. There it goes. Kind of. Of course, these are all RPN. But yeah, just some more advanced features on top of the 35 here. And then, of course, in 74, they come out with the HP 65, which is the programmable one, which I don't have. Or very expensive. Probably get one someday. What I do have is Texas Instruments answer, which is the SR52, which usually you can pick these up pretty cheap. I didn't pay much for this. Of course, these have the little magnetic cards for program storage. I'm not sure if it was this one or the SR51, and then Texas Instruments introduced their algebraic operating system, they called it, with the parentheses, trying to combat HP's RPN. So I think you can have up to 10 layers of nested parentheses. So we can do, I don't know, something, let's do parenthesis 1 plus 2, close parentheses, times 2. Yeah, I guess that was the wrong way to do it. I should have done it the other way. I should have done 2 times parentheses 1 plus 3. There we go. So lets you do order of operations without having to know RPN. Not that RPN is that bad, but this one does have a factorial key. So if you do that, you make the calculator think. So if we do something like 25 second factorial, so it takes about a little bit to come up with that. I think there's a line somewhere that shows that it's thinking. If we can see it. Yeah, so there's a line that shows up there on the side of the screen that shows that it's thinking. But there it is. A little switch for radians or degrees, but yeah. So anyway, my point is the mid to late 60s and early 70s. I think really a surprising. I should say, I won't say surprising, but each advance is strikingly different. To go from this to this in just 1 year. To me, at least, it seems like there's not that much striking difference in year-to-year advancements today, but we are getting to 5 nanometers, so so they're moving on from that. So a lot of those advances are behind the scenes now, but yeah. Anyway, so I think that's going to go it for this video. Finally have a working Bowmar901b, which is something I've been looking to get for a while now. See if it fits nicely in between all the other stuff that I have. Of course, still need an HP65 to fit in there, and of course a sharp micro compet to go on the other side. I do have one, it doesn't work right, so I think one of the MOS chips is dead in it. One thing else I forgot to mention, this uses 4 Lsi chips. So basically it's like discrete, I don't want to say discrete logic, but it's not a programmable device. The chips are, the logic for doing calculators, is, for doing calculations rather, was laid out on the chips, and the chips are made just for that purpose. They're basically ASICs, or what you call them. That's not what they call them then, but what do you call them now? They're ASIC chips, 4 of them, to do the calculator logic, versus this one uses a microcontroller. I would be kind of curious to see if you could find an unprogrammed one of those TMS microcontrollers. See what else you could program it to do. Kind of wonder how tied to calculators it really was. But anyway, so yeah, we enjoyed this video, and thank you for watching.